Hello, class. I don't know how long I can really do this lecture. It'll be one of the shorter lectures because I'm trying to do it in high definition so that I can show you the Smith chart right up close. And in fact, I've got it on a box. Happens to be a Dunkin' Donuts box. And I just wanted to point out things with the Smith chart. And I've actually drawn a couple things on the Smith chart. This would be my load right here. And in fact, I want to sort of draw in diagram form really what I'm doing here. So what we've got is we've got some type of source. That's our generator, our waveform generator someplace there. Then we've got a line that comes down to the antenna, right? I don't know how to draw an antenna. Yeah, there you go. There's an antenna. So this is going to be the load right there. And in fact, you see that the load that I've got here in our example is going to be 25 minus J15 ohms. That's what my load, complex load impedance is going to be. My characteristic impedance is 50 ohms. And so when we look at what the normalized impedance is for the load, we see that it's 0.5 minus J 0.3, right? And I've actually, on the Smith chart, made a dot right there. That would be Z of the load right there. And where is that? That is at the load, isn't it? That's Z of the load right there. Does that include this line from here to here? No, it doesn't. Does it include the, no. Although we know that this line here has a constant characteristic impedance. So we know that the voltage standing wave ratio along that line is going to always be the same. And that's what I have here, and I described that in our last lecture. This is my circle of constant VSWR, right? That's my constant VSWR. You can see that the impedance all the way around here is going to be all different, but if we put it into the VSWR equation, it'll always come out the same constant VSWR. Not only that, from the Smith chart, we can actually use the scales at the bottom. And this is one thing I want to point out, to go into a little more detail on the Smith chart. With the Smith chart, this constant VSWR circle, if I was to like measure it out over here and then drop a line down, what do you know? I've already done that. And drop a line down from that point all the way down to the scale down here, you can see a couple things with the scale. If I look at the scale, you see that this line right here is the reflection coefficient. That's right. This line is the reflection coefficient. We can read the reflection coefficient right off that line. And in looking at it right here, I see the reflection coefficient is 0.39. So my reflection coefficient is going to be 0.39. Now, what would my power reflection coefficient be if my reflection coefficient is 0.39? Well, that would just be the square of that, wouldn't it? So 0.39 squared gives me 0.15. So 0.152 would be my power reflection coefficient. You know, another thing that we can read right off here is my return loss, right? My return loss in decibels, because the return loss in decibels has everything to do, as I explained in the last lecture, has everything to do with the reflection coefficient and the VSWR. So once you know the VSWR, right, and the reflection coefficient, you also know your return loss in decibels. And I am reading off here, it is 8.2. Okay, so my return loss equals 8.2 8.2 or minus 8.2 decibels. Let's say that. That's what I'm losing due to the reflection coefficient um, at the load. All right, now I can also read off my VSWR. Although I could read my VSWR off here, I could just read it over here. That would be my VSWR. You can also read it down here, which is a little more exact scale, and that gives me 2.25. So VSWR 2.25. So I've got all of those things because they're all interrelated. I've read all of them off my little scale down here, but you've got to remember that the reflection coefficient is a complex number, right? So I know what the magnitude of it is, 0.39, but what is the angle of the reflection coefficient? And as you can see, that's why I drew this line all the way through the outside circles here, because I don't know if you can actually see this. You might, it's coming through pretty close though, or pretty well. This says the angle of reflection coefficient in degrees. Angle of reflection coefficient in degrees. All right, so that's what we need. So if I follow this around, angle of reflection coefficient in degrees, and I follow it all the way around to where it goes across here, you can see it's between 130 and 140 and much closer to 140. I'm going to say that that's about 138. So my reflection coefficient is 0.39 at 138 degrees. Does everyone see how I took that reflection coefficient right off the thing? Okay, good. That's good. Now, I want to also look at a couple of the other things that are down here. If I look over here, just to explain the Smith chart, right? If I look over here, let's just think about the Smith chart. The Smith chart is a half wave. All the way around the Smith chart is 1/2 wave length. If I go halfway around the Smith chart, that's a 1/4 wavelength. And why is that? Because every half wavelength, the whole thing repeats itself. Okay? Every half wavelength, the whole thing repeats itself. So we only need a half wavelength here, don't we? And this, the furthest out circle, is the wavelengths toward the generator. Now, what would that be? Well, let's say that we're right here. Let's say we're examining the antenna. Well, then that would be the wavelengths toward the generator along the coaxial line here, wouldn't it? The wavelengths toward the generator. What if, on the other hand, I wanted to put something here right off the source, and I was looking, I actually could determine the whole composite system, right? The impedance of this whole thing, and I said, well, that's the load. Well, then I could put something in there, and I might have to actually move it toward the load along this line that I've got there. That's not usually how you do it. But anyway, we can do one of two things. We can put components in series in that line, or what we can do is we can put components in parallel with that line so that there's a certain harmonic that occurs with the waveform going up there and then re-interacting with the waveform at that point. And then how far from the load in wavelengths should I put that stub, that parallel stub, right? This would be a series stub, and this would be a parallel stub. So that's what we want to find out. Now, here's what we've got. Another thing I want to point out about the Smith chart is that on exactly the other side of the Smith chart, let's say this is my impedance, my normalized impedance, 0.5 minus j, 0.3, right? That's Z sub L, small z sub L, normalized impedance. On the other side of the VSWR circle, if I were to read this off, which is Y sub L, and that's the admittance, equals 1.5 plus J 0.85. So that would be the reciprocal of 0.5 minus J 0.3. It's close to it. It's rounded a bit, but you get the idea. I think it's actually 1.47 plus J 0.88, but you get the idea. It's pretty close. I couldn't draw the circle close enough. So that's my admittance. Now, why would I use the admittance and try to match the admittance rather than matching the impedance? If I'm going to match the impedance with a series component, then I would try to match the impedance, and I would match the impedance from the source to the antenna and the wire and everything else. I would match the impedance, right? If I'm going to put this some type of series component in there. But if I'm going to put a parallel stub in there, I do not want to bring the impedance back to the center. I want to bring the admittance back to the center. I hope everybody can see that. Admittance for parallel stub matching, impedance for series stub matching. All right? It just makes it so much easier to use the Smith chart that way. Okay, so let's say that I've got this and I know that I'm using, well, let's look at a frequency. What if I was using, this was a coaxial cable, and I know that the velocity of propagation of the coaxial cable is about 195 times 10 to the 6 meters per second, right? Well, let's say that I had a frequency, because we know that this equals frequency times wavelength. Let's say that I had a frequency that was 19.5 megahertz. Then how long would my wavelength be? I think everybody can see my wavelength would be 10 meters, wouldn't it? Right? Because F times lambda equals my velocity of propagation. So my thing would be 10 meters. Now, let's say that I had this line right here. I just wanted to find out what is Z right here. I want to find out right there, and that is going to be, I'll just come up with a number. Let's say L back from the load to this point is 2 meters. I want to find out what Z of L is. What is Z of L? How would I find that? 2 meters back from the antenna heading toward the source. How would I find that? Well, right here we have wavelengths toward generator, don't we? And isn't that from the load toward the generator? You know, we've got another one here which goes the other way. This one is going this way, and this one says wavelengths toward load is going this way. Does everybody see that on the, hopefully the Smith chart that you already have? I think I've sent them all out to you. So which way am I going? Well, I'm going toward the generator from the load. At this point right here, I'm going back toward the generator. So I want to go toward the generator, and I want to go toward the generator 2/10 of a wavelength. Well, where am I now? Well, let's see. Right now, I would be right about here, right? And that says it is 0.442. 0.442 wavelengths. Right there. And I think everybody can see that this repeats itself. It goes up to 0.5. Right at this line, it gets to 0.5. And yeah, right here. gets to 0.5. And why is that? Because there's, I mentioned before, the one trip around here is 1/2 of a wavelength, and these are in wavelengths. So if I'm going from 0.442 and I have to put in 2/10 of a wavelength, well, then this is really going to be 0.642, isn't it? 0.642, well, there is no 0.642 because it only goes up to 0.5. So wouldn't I have to go up to 0.5 and then go another 0.162? So I'm going to go another 0.162 right up to here. Oops, forgot. That whole thing doesn't go on there. Right up to there. So this is what I've done. In that extra 2 meters, I have actually added on to the wavelength, right, this much. That, by the way, is still only 0.2 of a wavelength, isn't it? 0.2 of a wavelength, and it brought me all the way back down to here. Now, if I take a ruler and I go straight back down to the center from there, where I'm crossing the constant VSWR circle, that is going to be the impedance, the normalized impedance at that point as I've gone back, right, back to this point here. Let's call this point A, and this is point B. As I've gone from point A back around to point B, I've changed the impedance because I'm going along this line, right? And so now I know what the impedance would be right at that point, that far along the line. And I could do something, there if I wanted to. If I, really the salient point to get to, I'm just going to draw it in here, is really this point here, where I'm at 1 plus J0, right? This is 1 plus J0. Well, this is 1 plus J something or other, isn't it? But if I can get to that point, then what I can do is I can put a stub in there that will take me back down this line eventually to get to the center. And that's what we really want to do. And with a series stub matching, we would want to come around here to that point, and then we would want to put in a stub right there that would bring it back down to this point. I'm going to do an example in the next lecture, and I'll probably use this here anyway, to actually show you how to do a parallel stub matching. And instead of using impedance, we're going to be using admittance to figure out how far back from the load we should put the stub, and then how long we should make the stub. All right? Okay. That's going to be our next lecture. And since I'm doing this in HD, they can't be real long, but I wanted to show you anyway, how you would use the Smith chart to then look at if, you're going back from the load. Well, there you go. I'm back. There isn't a line to go back from the load. There's a line to go toward the generator. Oops, now I've screwed up the whole thing. I had to, come on. There we go. I had to do it in HD and in variable focus for that, but everything seemed to have come out pretty good. So let's do a parallel stub matching example.